Now, for the last presentation of the day, Caitlin Ahrens has been a museum family member for a very long time. It's so nice to have a connection with an astrophysicist Pluto manager. And I have been trying to bring her back each year to be the liaison with Commander John Harrington and Dr. Jose Hernandez. We're wearing masks again. She's across the country for me. But with that, I would like to introduce the most wonderful Caitlin Ahrens.
Hi, everyone. Hi, Charlotte. Thank you so much for that introduction. I hope you can hear me.
I can hear you, and I see you in my brain.
Fantastic. All right. So thank you so much for still allowing me to talk about all the awesome space that's been going on. I'm sorry I can't be there in person. The world is still crazy. But what's fascinating, though, is, thank goodness for technology, too, is that we're still able to share ideas and share our journeys, especially our STEM journeys, our science journeys together. And that's what I want to emphasize for my presentation today is what are the lessons learned through a little bit of space exploration that in itself can take hours and hours and hours to go through. But for the sake of brevity, I'm only going to touch base on a little bit of the moon and a little bit of Mars. But in that case, what have we learned as a science community? What have we learned through our journeys of working together? And some of it worked, some of it didn't. And from those lessons learned, how can we look forward? So let me share my screen. Oh dear. Okay, there we go. My computer didn't like that there for a moment. Okay, so looking backwards to then move forward in space exploration. Okay, so hopefully that'll work. Yes, all right. I'm also going to be using a lot of fun GIFs from Back to the Future because that's one of my favorite sci-fi films. And it really does come to heart as to all the technology that we have. How do we move forward? So, like I said, I'm going to be touching a lot about the moon. Now, when I show pictures of the moon, and you see the near side of the moon and the far side of the moon off to the right here, if I were to just ask you, what's the first thing you notice? I usually gotten similar answers, but some of the answers I've gotten is, you got these much darker, patchy, what we call mare areas on the near side versus the far side. Maybe you notice that the texture of both sides of the moon are different. In which case, you would be correct. Yes. So as different shades of gray as we have here, in reality, the science of the moon is just so fascinating. There's still so much to be learned with the moon. And a question I get asked often is, why do we keep going back to the moon? And I'll be answering that question later in this presentation. But of all the missions that now, when I ask you, what do you remember about lunar missions? A lot of people remember the Apollo missions. Those were very prominent. But to get to that point of Apollo missions and technology of the 60s and 70s, we really had to understand, how do we even get to the moon? And that was the bulk of the 1950s and early 60s. So just all sorts of craziness with this figure here. But we had quite a bit of exploration. Apollo in the darker blue here, Surveyor missions, Chang'e is the more recent, and then all of the Soviet Union into current Russian Luna missions as well. So we've had just a wide swath of missions, and this actually doesn't cover all of it whatsoever. So our first attempts were the Luna, and Pioneer 4 was an interesting design choice in 1959. So just from 1959 and 1963, we were still more in the engineering stage. We were more in the let's just build something just to get to the moon, and if it works, good for us, and if it doesn't, well, okay. And again, a lesson learned, specifically with Ranger 4. Ranger 4 crashed on the moon. Oops. And so by crashing on the moon, though, we do not call this a failure. We never call anything a failure by any means, because we're constantly learning. Why did it crash on the moon? And then even crashing on the moon, did we get any kind of data, any kind of results from our own engineering perspective and also from our own scientific perspective? Looking at it from the engineering perspective, it crashed on the moon. Okay, did it send back? Was it able to send back anything? Not really. But that's still results. That's still data for us. In a physics point of view, how did it crash on the moon? What was the orbit? Could we fix our trajectory? And then another physics too. How fast did it crash on the moon? Which is much farther down in this newspaper article that I have. But nearly 6,000 miles per hour. That's a bit of a projectile to crash onto the moon. So like I said, physics, we definitely have learned with Ranger 4. Okay, let's fix our orbit just a little bit, shall we? So from those Ranger missions, it's just kind of like, okay, we've got work to do. We need to be better about our designing. We need to put more cameras on our instruments. There for a while, we didn't have cameras. It was just simply a little beacon of, hey, I'm at the moon. I'm at this altitude above the Earth, or I'm at this altitude above the moon. And whether they crash on the moon or they eventually orbit or just die out, that's all we got. So how do we better ourselves with putting cameras on these things? So we found this huge boom of missions all of a sudden. So thanks to actually Zond 3. So Zond 3 was from the Soviet Union. We've still had a couple Luna and Ranger missions to mostly soft land on the surface and take as many pictures as they can before they go kerplunk right onto the surface. But Zond 3 really was the highlight camera that started everything. So since Zond 3, then we're like, oh, let's create orbiters. So now we have the lunar orbiters. Unfortunately, they didn't last long. We had the surveyors. They lasted a pretty long time. So from combination of orbiters and surveyors, we were able to realize, okay, there's a lot of nice, smooth, dark Mare regions on the moon that we can potentially land people at. Let's figure this out. Let's test ride to get to the moon. So test riding was mostly with Apollo 7 and 8. Make sure we're able to get to the moon with a much larger capsule. We're able to orbit safely, and then can we bring it back to Earth? Because obviously you don't want to strand any astronauts. So finally, with Apollo 11, we made our landing. And then from somewhat sequential Apollo missions, since then, we've been wanting to land more people on the moon. So with Zond 3, these are the images I'm talking about. So in our day and age, we're like, oh, that's kind of low res though. But you figure though, Zond 3, it was just at the early stages of 1965. That's really good imagery for 1965 on a spacecraft to the moon. And so Zond 3, we don't really use images that much anymore, except mostly for science communication purposes. But for Zond 3, it was really quite spectacular and really started our use of cameras. So then we have Surveyor 5. This, again, the use of cameras on landers now. And for cameras that have actually survived the landing on the moon is another spectacular feat. So in that case, we were able to see, oh, the moon is not this incredibly smooth, natural satellite of the Earth, but instead somewhat rocky, very granular, very gravelly, and that could be potentially dangerous for eventual landing of humans. Excuse me. So we finally have our beautiful parade of Apollo missions to really get our foot on the ground, almost literally, to the moon with much better instruments. It's no longer just let's take a camera, we go to the moon, take pretty pictures, and then back to Earth we go. But the Apollo missions really gave us a sense of let's collect samples and let's do some experiments on the moon. And these experiments can range from putting mirrors on the moon, and we would zap lasers from various areas around the Earth. Those lasers can then bounce off of those mirrors, and then the laser would bounce back right back to us. And that way we can actually tell, like, not only range, how far away is the moon from Earth, and then you can time how quickly does the laser bounce back and forth. You could also tell that the moon is actually very, very, very slowly moving away from Earth as well. So those type of instruments were really fun. We also had seismometers because we want to know about moonquakes. Why not? It's a natural satellite of Earth. It certainly does not have plate tectonics, but it has a gosh darn lot of craters. How do the energy, the powerful energy off of those craters, how does that energy disperse through the surface? In which case, you would cause moonquakes. So we would have seismometers from the Apollo era as well. So just looking at all the Apollo landings in gold here, notice most of them are truly around the darker Mare regions, mostly around the equator, though. And that's because it's much easier to land on the equator, and that goes for any planetary body. But all the pictures from Apollo, I could just show for hours and hours and hours. Anything from the geologic features of the moon, so we were able to see valleys and mountains. Just looking at the tracks and the footprints left by the astronauts, we were able to get a sense of a geologic aspect, and even a little bit of the chemical aspect of the soil, the lunar soil. How soft was it, or how powdery was it? How dusty was it? How gravelly certain areas were compared to some other different areas. These are taken by two different Apollo missions, and you can see the texture of the surface where it was fairly smooth. It looks like a very sandy beaches, whereas this one's more of a chunky gravel mix of rocks here. This one was fun. This one was from Apollo 17. This is the mystery of the orange soil. So this is not necessarily color corrected image though, but enhanced image, if you will, just to bring out some of this this rusty coloring. So what was going on here is astronaut Harrison Schmitt was playing around in the dirt as astronauts would, and he noticed, oh my goodness, wait a moment, why is this soil orange? What is possibly going on? Why is it orange? Everything else is either gray or dark gray or lighter gray. You truly have different shades of gray. Why is this orange? And it was fantastic. It was like, oh my goodness, put it in a baggie, keep it sealed. We're gonna bring it back to Earth. This is gonna be great. And then they bring a sample back to Earth. They open it in the lab, and this is brown. It's just brown and gray. And they're like, wait, what happened? It was orange. We swear it was orange on the moon. And they're like, wait a minute, could our eyesight have been weirded out, like at the moon? Like, was this more of a physical or mental gobbledygook going on here? Like, what's going on here? And turns out, looking at that orange then turned brown soil, it wasn't that the soil changed colors. It was actually because of you got to have the right amount of sunlight to reflect. So certain rocks in nature, if you look at a certain rock a certain way, it may appear green, but then you angle it a certain way, it may appear blue. So very much similar to this way, where you have soil in a certain angle of the sun, it appeared orange, but then when they brought it into a lab with no sunlight, it was very much brown. Now, why it was orange was very fascinating. What they found was actually why it was reflecting orange, rather, was because it had glass. It had volcanic glass. So this was a really cool sample to bring back to Earth because it then gave us a look at, oh my goodness, there were not necessarily volcanoes on the moon. There's not these big, giant, towering rocks of smoke and lava at one point. No, nothing like that. Nothing that extreme. But rather, pools of lava that would just ooze out of the surface of the moon and create these beds and layers of lava, of lunar lava. And so, what astronaut Harrison Schmitt brought back was some of that lunar lava. So pretty cool. So from those hand samples, we have collected hundreds of kilograms of samples. Now you may think like, oh, okay, a couple hundred kilograms and all those Apollo missions, that doesn't really seem like a lot. But in any case, it was, it got pretty hefty. It got pretty heavy to bring back all those rock samples, though. So it can definitely take a toll on bringing samples back, and safely, too. You don't want to contaminate any of these rocks. You want to try to keep them as pristine as possible. Also, pictures of all these hand samples and what I'm about to explain here are freely available. I have some links at the end of this presentation, and I also gave some resource links to Charlotte as well. So those will be freely available for everybody. Not only do we have hand sample pretty pictures, you can look at rocks all day. I know I love to. But also you can actually cut open these rocks very, very, very thinly sliced. And I mean thinner than deli turkey at this point, and very thinly sliced. And what you do is that you put it under a specific type of microscope called a petrographic microscope. What a petrographic microscope does is that it shines a specific type of light under your glass slide. What it does is that it reflects what's called birefringence. And birefringence of different types of minerals reflect and essentially refract different colors. So these are actually different minerals in the same sample of a meteorite. So the different colors that you would see here would be the different minerals. They're so fun to look through, and there's hundreds of these completely freely available to look at online. They're completely freely archived. So after the Apollo missions, that was pretty much the boom of lunar exploration. And it kind of took a bit of not necessarily a nosedive per se, because we still wanted to dreadfully go back to the moon, but it was still just a matter of funding. It was, unfortunately, politics got in the way. It was, why should we go back to the moon? What else do we even need to do at the moon? So there was a lot of talk back and forth, like, do we really need to go back? The answer is always yes. But in any case, you have the Luna missions still going strong from the Soviet Union. Skip all the way to 1990, you have the Hiten mission from the Japanese Space Agency, and then Clementine. So Clementine from NASA was kind of like our like, okay, we're kind of making a comeback here. Clementine was a sweet little orbiter taking mineral maps of the moon. So now we wanted to get a sense of what types of minerals, what types of rocks are we actually looking at. Yeah, we now know that there's lunar lava thanks to Apollo 17 and the mystery of the orange soil. But what else can we know about the rocks? So that's what Clementine was about. And now we're finally getting into the age of the orbiters. A lot of orbiters. So Lunar Prospector was a really fun mission, and I'll talk about Lunar Prospector here in a bit. I'll just talk about it now. So Lunar Prospector was similar to Clementine. It kind of gave us a sense of what types of rocks are we dealing with. The SMART missions, Kaguya, later named Selene, also from the Japanese Space Agency, was a great mission. Changi 1 and Changi 2 were starting to be the orbiters. Lunar Reconnaissance Orbiter finally began its journey in 2009. I'll get to the Lunar Reconnaissance Orbiter here in a bit. But what the Lunar Reconnaissance Orbiter had was a very, very fun little package, I should say, and it was LCROSS. So LCROSS was a very fun bit. So LCROSS was not necessarily Lunar Reconnaissance Orbiter. It was mostly with Lunar Prospector to drop LCROSS, but then Lunar Reconnaissance Orbiter, thankfully, was just there to watch the drop. So what LCROSS was a purposeful impact into the south pole of the moon. And what LCROSS did was this little projectile would slam itself into the moon just at a specific angle and speed to make a plume of material. Now, you might go like, well, okay, we just shot the moon. Good on us. Why did we just do that? But why we wanted to do it was LCROSS excavated that subsurface material. So in doing that plume, all that plume material was whatever was just dug up from the LCROSS missile. And what it did then was cross between Lunar Prospector, you had a Lunar Reconnaissance Orbiter, and you also had telescopes on Earth all watching this plume. So it detected temperatures, we detected different kinds of chemicals, we detected different kinds of minerals, we detected ice from LCROSS. And so using that purposeful bombardment into the moon really gave us a good sense of, oh, there's some really weird chemistry going on just under the soil of the moon. So that was fascinating as well. So here's a little cartoon of Lunar Prospector dropping LCROSS, and there went LCROSS. So yeah, so there goes Lunar Prospector. So LRO began in 2009. It's still going strong. We still use LRO, Lunar Reconnaissance Orbiter, for much of our lunar mission planning, and a lot of cool data with the moon as well. So I'm actually on the Diviner science team, but you also have Crater, LAMP, LEND, LOLA, LROC, and Mini-RF. So all these different kind of instruments do different types of stuff. Yeah, there we go. So Mini-RF is our radio frequency. So this helps with communications, but also helps with, do we get any kind of interference from the sun? That would be some interesting data there. DLRE is Diviner, which is the team that I'm on. So this looks at the different kinds of temperatures on the moon, and temperatures can really tell you a lot about the soil, about the different kinds of water, different kinds of ice at the surface. So temperatures galore. Let's see, what else do we have? Whack and Knack is our fancy cameras, wide angle camera and narrow angle camera. So not so fancy of names. LEND is the neutron density. So this gives us how much hydrogen is at the surface, and that hydrogen can then tell us where is the water. LOLA is our altimeter, so it gives us our elevation maps, and then LAMP gives us our what's called our Lyman Alpha mapping project. So LAMP gives us more of the chemistry involved as well. Oh goodness, hang on, my computer is kind of freezing on me. Oh, there we go. Okay. So all of this data, you can look at essentially the same part of the moon, but in different lenses, using different kinds of data sets. And that's what's very fascinating about the Lunar Reconnaissance Orbiter, is it's almost like you're looking at a certain area through different filters. But with those different filters, we all have to kind of talk to each other. So I mostly work with infrared, a little bit of the sunlight data, but mostly the infrared, because then that can tell you your temperatures. But also water ice really is bright in the infrared. Neutrons, you deal with your hydrogen. Ultraviolet and radar, you kind of deal with the different types of chemistry like thorium. And then elevation is very important, especially with mission planning, because if you want to land a rover or a lander, you kind of need to find a nice flat area to land. Oh dear. There we go. So this is what I mean by a little bit of the neutron counter. This is part of the lunar South Pole. So all the darker, bluer areas are where we get a lot of the water ice, or supposedly water ice. This is where most of our hydrogen neutron counts are. So we just kind of extrapolate and go, oh, if there's a lot of hydrogen in those areas, there's probably frozen hydrogen H2O. So this is what some of the sunlit maps I look at. So all the darker areas that you see here are areas that really take the phrase where the sun don't shine to almost a literal level. So there are areas at the lunar South Pole and somewhat on the North Pole as well that truly do not get any sunlight. And then here's some of our beautiful mare areas. So this is all cooled, frozen, solidified lunar magma, lunar lava. We have riles and we have pits and we have caves. We have beautiful craters. So the moon really gives us a lot of really cool stuff to work with. So from the Lunar Reconnaissance Orbiter, it kind of spiked into a resurgence since 2018 with a whole new level of extra missions. So Luna missions are still going strong. The Chang'e missions, especially 4 and 5. Chang'e 6 is certainly underway as well. Selene 2 unfortunately got canceled. Selene 3 is definitely underway as well. Chang'e 4 had some very exciting prospects. Unfortunately, it didn't last long. But Chang'e 4 actually had a little biodome where it was growing cotton seeds. And unfortunately, a leak happened. Unfortunately, a leak happened in the biodome. Now, Chang'e 4 landed on the far side of the moon. So far side can still get pretty cold on a daily basis. But the problem with where it landed, though, is that it got incredibly cold, like way colder than -100. So pretty cold. So unfortunately, with that leak into the biodome, it just absolutely froze out their cotton seeds. So unfortunate. But again, it's never a thing as a failure. It's only learning from our mistakes. What caused the leak? How could we make those biodomes better and more sustainable? Could there have been better tracking of leaking? Could there have been a way to maybe do like a double enforcement to prevent even further leaking? So it's, again, there's always something to learn from those. So future work is certainly Artemis, and I'll talk about Artemis here in a bit. There's also 2 missions that I'm aware of. There's a lot of lunar missions to be coming up, though, but 2 in particular that are very exciting are Lunar Trailblazer and Viper. and I'll talk about those later. But we also have the Luna 27, 28, and 29. So Luna is still going strong. Obviously no longer Soviet Union. Now it's called Roscosmos with the Russians, and they're wanting to also go to the far side, but also mostly to the South Pole Aitken Basin, which is this lovely bluish green area of the moon. So Artemis 1, 2, and 3. All right. So the mid 2020s into the 2030s are going to be very exciting for the moon. So Artemis 1 is essentially going to be uncrewed. It's going to be our flight test. So very similar to the early Apollo missions. In this case, it's just going to be a flight test. It's going to be our dress rehearsal. Artemis 2 is then going to be the first crewed flight to the moon, hopefully to the south pole of the moon. We haven't picked out a landing site just yet. That is still being discussed. Woo. And then planning is certainly underway for Artemis 3, and then hopefully we can keep up a cadence somewhat similar to the Apollo missions, probably not as rapid as time spans, but certainly keep up some sort of cadence of future Artemis missions. So why the south pole of the moon? I said earlier that the equator is much easier to get to on the moon. Why in the world, or in this case, why in the moon, are we even going to the south pole of the moon? Well, the South Pole is weird, to say the least. You have certain areas called permanently shadowed regions, or PSRs. So PSRs are where we have more likely ice. These areas can get quite cold. This is a summer map. Now, when I mean summer map, I promise that the moon is not on fire in this picture, but rather the warmer colors are the hotter temperatures. It's still pretty cold, but about room temperature is probably the orangish areas. But notice the really dark bluer areas here. You're getting into way past negative 200 degrees Fahrenheit at this point. Very, very cold areas. This is a winter map. So the very cold areas are in the very dark blues and purpley areas here. But notice I said ice. I actually didn't specifically say water ice. It's not just water ice. So we can't just go there, mine the ice, and then drink it. You most definitely do not want to do that. It's not just water ice here. So this is diviner data. So like I said, this is the type of data I look at on a daily basis. So a lot of the bluer areas, yes, there would be quite a bit of water ice. But keep in mind in the darker blue and the purple areas, you're more than likely also to get ammonia, sulfur dioxide, maybe even formaldehyde, carbon dioxide, and hydrogen sulfide. So you definitely don't want to get those type of ice cubes in your iced tea anytime soon from the moon. So yes, we have the Artemis missions. Lunar Trailblazer, like I said earlier, it was selected, I want to say just a little over a year ago now. So a fairly new mission selection for the moon. So Lunar Trailblazer is going to help us map out all the really cool water spots and just ice in general. And then Viper is going to be a little itty bitty rover to land near the south pole of the moon. It actually just selected its landing site just a couple weeks ago. It's going to go near the Nobile crater. So very exciting. So Viper is actually going to have a drill. And I love its logo to death. So you could actually see the drill here in the middle of the V. But what it's going to do is going to drill into the soil just a little bit and actually see, does the ice change with depth into the lunar soil? And we're still looking at the samples. So Apollo, we never stop with Apollo. So those samples are still being discovered and still being used. So fairly recently, there was a really neat article about unopened Apollo samples. And yes, we still have them. We still have unopened samples. So very exciting. So asking the question, why should we go back to the moon? So the Earth is the only terrestrial planet with a natural satellite. And you have tidal pool physics, you have volcanism, you have ice. And it's truly just scratching the surface as to, all the cool stuff that's on the moon. But that's just the surface. But we want to know how and why. How and why did the moon become the only natural satellite of the inner planets? How and why did it form tidal pool with the Earth? How and why is there volcanism on the moon? Why didn't it form these giant volcanic mountains that we have here on Earth? Why instead does it just have like little puddles of lunar lava? So I'll chat real quick about Mars. So this is what we call the Mars Family Portrait. It's a really spectacular poster that you could actually freely download on NASA websites as well. You just Google Mars Family Portrait and it'll bring you up to this. You could actually zoom into it with much higher resolution. Obviously, I can only fit so much on a PowerPoint slide. But Mars has had its fair share of orbiters and flybys and landers and rovers, all sorts of stuff. But it doesn't come without consequences. And I'll just give two examples. There's plenty other examples, but two mostly citable lessons learned. First one being the Mars Climate Orbiter from NASA. This was 1998. And then the Schiaparelli lander from the European Space Agency, ESA, back in 2016. So both of these would have been really interesting. Mars Climate Orbiter would have, as the name suggests, the orbiter for the purpose of looking at the climate. Methane comes in spurts and bouts around Mars, and we want to know why. And there's a season with carbon dioxide ice on Mars, and the poles on Mars grow and shrink, and we want to know why. Schiaparelli lander would have been one of the first ESA landers with Mars. It would have done similar projects to that of the Phoenix lander from a couple years back out of NASA. Now, why I'm meaning lessons learned here is because they both did not survive, but in completely different ways. So Mars Climate Orbiter, we had the unfortunate accident of missing our trajectory entirely because we did not convert units well. This is our problem with not using the metric system. So we had a big whoopsie with Mars Climate Orbiter, and it completely missed its orbit entirely. So it essentially just skipped like a rock on a lake. It just skimmed Mars, and eventually it crashed. Schiaparelli lander, it very much crashed. It did its trajectory just fine. It was coming in just a little too hot, unfortunately. And what happened is that when you come in at a certain angle and you come in a little too fast, it's not a good thing when your parachute rips off of the lander, because otherwise it's going to, go kerplunk, as the picture here suggests. So all these like little bright spots that you see here are the different pieces, reflective, shiny pieces of the lander. And I think one of them is the parachute. So, whoops. But again, not necessarily failures, but just always some sort of lesson to be learned. So we now have two future Mars missions, but this is ESA Roscosmos with the Rosalind Franklin rover. This is part of the ExoMars 2022 initiative. And then eventually sample return 2028. I should have a big old question mark with the 2028 because we don't have an official timeline with the sample return. But what this does is that this works in part with the Mars Perseverance rover, Percy. And what Perseverance is doing is that it's tagging. It's almost like geocaching on Mars. It's tagging certain rocks and rock cores for eventual, almost like Amazon picking it up and bringing it back home for us. So why do we keep going to Mars? It's the only other terrestrial planet besides Earth with an atmosphere and a climate. Now, you can argue and say Venus, has an atmosphere, but the atmosphere of Venus is incredibly dangerous and such a wild beast. of an atmosphere that it's kind of in its own category. So in this case, it's a somewhat regular atmosphere with Mars. There is a little bit of a climate. It has metal reservoirs. It also has subsurface water reserves as well. And we want to know how and why again. So looking forward into the other parts of the solar system, what about the Voyager era? We've certainly learned a lot with Voyager. It got to Jupiter in 1979. It made it all of its way to Neptune in 1989. So it kind of gives you a nice scale of the solar system, right? Going from 79 at Jupiter all the way out to 89 at Neptune. It was just going full speed. Never got to Pluto because the orbit of the planets just didn't. It lined up perfectly for the 4 planets here, but not with Pluto. Pluto was on the other side of the solar system by then. But Voyager, with it being our interstellar probe, now that, since 1970s, certainly 1960s, when it launched, our technology has completely changed since then. Are there any plans to do a Voyager 2.0? And the answer is potentially with Interstellar Probe. So Interstellar Probe is still what's called a mission concept, but there's a lot of exciting resources with Interstellar Probe. I highly encourage you to go Google Interstellar Probe. It's with the Applied Physics Laboratory, APL. And then we're also going to Venus. There are 3 planned missions to Venus, Da Vinci Plus and Veritas, and then Envision with the European Space Agency. So many missions all at once, and they all were announced to go to Venus back in June, like truly within a week of each other. It was like, we're going to Venus, we're going to Venus, we're going to Venus. Okay, we get it. Okay, we're going to Venus. Why in the world are we going to Venus? Well, like I was saying earlier, picking on Venus is that its cloud system is just on a whole different level than any other planet in the inner solar system. It's also spinning backwards. Its north pole is actually facing south. There's over 400 volcanoes on the surface of Venus. Are they still active? Are they not? There's potentially lightning storms on Venus, but we don't 100% know. So all of the stuff with Venus, there is still a lot to be said and done with Venus. So this was pretty much our entire take of, oh goodness gracious, we have a lot to learn about Venus, but we've learned so much about the other planets. Can we use some of those instruments and use some of that engineering, that ingenuity, to strap onto a rocket and take it to Venus? The answer is yes. So thank you so much again for having me here. Thank you, Mona group, for having me chat with you guys today. Keep an eye out for International Observe the Moon Night in 2021. That is coming up. That is already next weekend. It's October 16th. So join NASA for a global celebration of observing the moon night. And there's a couple links here, but there's a fuller list of links that I gave to the Mona group, though. So happy to answer any questions if there is time left, but thank you so much again.
No questions at the moment. Thank you.
Thank you. All right. Well, so I'll just extend my thanks again for everybody listening in, and just keep looking up, because goodness gracious, there's still so much to be done. There's still so much to learn. Are we going to probably fail learn a few more times? Yes, most definitely. As long as we're safe about it, that's the key. But there's always going to be challenges, and that's the fun part.